Principle of moments is what we are going to see in this lesson and how we can apply it. It states that the principle of moments states that when a number of system of coplanar forces act, coplanar means they are in the same plane, acts on the body, comma, the algebraic sum of moments of these forces about any point is in the plane is equal to the moment of the resultant of those forces about that point. So the idea here is the resultant force, the moment of the resultant force about that point is equaling to the the moment of those forces about that same point. So let's see how we apply this example, that idea. Find magnitude, direction, and the distance of the resultant of the following forces. So this is part A. Now the first thing, we know that always the distance of go to get a moment, we need the result of the resultant, we need the resultant itself, then times the distance from the point where moments were taken. So from here, we start, this force is 3 and this one going up is 6, meaning of course the resultant is going to be going upwards because this one is bigger than this. So in that order, first of all, we can assume this is going to be, we are going to take moments about A. So if I assume this is my point A, it means that I'm going to be having my resultant going up because we start going to act in this direction. For a distance, I don't know, which I'm going to call X from there. So you know that always, and from here you can start my resultant is going to be now 6 minus 3, which will be a 3. From there, you know that our, now taking moments about A, you start this point, and take moments about A, this one is going to be anti-clockwise. So taking moments about A, anti-clockwise, from here, instead we are going to be having here about A, I'm going to be having R times X equaling to the moments here, from here, so this one is going to be now 3 times 0, then plus. This one is going this side. It's going to be 6 times the perpendicular distance from this point, which is 3. So, it told us that the resultant times the distance, to get the moment of this resultant, we get this perpendicular distance, then times the force, which is R, then perpendicular distance is X. It's going to be the same as the sum of moments of this, about the same point. So sorry, I'm getting about A, then here about A. But our R is 3, so I have 3x equaling to 18, and so my x is going to be 6 meters. So meaning, therefore, the one way to get the magnitude, so my R is equaling 3 Newton, that's the magnitude. Direction, you see that we are taking, I think you see, in that direction, anti-clockwise, but in the direction, or you can say the direction of, in the direction of the 6 Newton's force, 6 meters from A. As simple as that. Even if now someone can say, what if I take them from here? No problem, you take them from here. If you take them from here, now this is going to be from here. If I take them from here, now it's that they are going to be clockwise. I'll be having 3 times this, which will be 9, then you get the distance. It's up to you. Then you also substitute there. That's okay. Then when you come to this, you see here, because this is not a couple. Okay? This is not a couple. Okay, but let me put alternative. This is not a couple that they have to be the same. Alternatively, someone can say, now, still the resultant is going to be 6. Our resultant is going to be 3 Newtons. And now, let us take moments now about B. Now, we take moments about B. Let me take them anti-clockwise still. These are my resultant times, now my resultant is going to be in this order. So if I'm taking moments about B, means that this is going to be the B. Then my resultant is going to be R, and this distance here is going to be X. So here, where you take moments from is going to define the distance. Okay, so my Rx will be about B. You take B, it's going to be now, because 6 is there, 6 times 0, then plus 3 times this distance, which is 3. So my 3x here is going to be 9, and so my x is going to be 3 meters. What does it tell us? It means that now my R is in the direction of, still, now this is the direction. If the direction is this, it means the direction of, but now this one is going to be the direction of this force. And then from, if you take moments about B, the distance is 3 meters. If you take moments about A, the distance is 6 meters of there. Okay, so it's up to you. Okay, let us come to this now. Start from here. Our resultant is going to be acting downward. So resolve in that order. You see now all of them are in the same direction. So I'll be having now 2 plus 8, which will give me 10 newtons. Here we are resolving upwards. Okay, so it's that now I have this now, means either you take, it means that R is going to be acting in that direction. So either you take at A or at B, but let me take at A. So if I'm to take at A, then my resultant is going to be in that order. If this is A, then from here, let me call it X up there. So it means that now my Rx, if I take them, it's that way I'm taking them, I'm taking A, but it's going to be clockwise. So at A, clockwise, Rx is going to be, when we come at A, here, this one is going to be 2. It does no perpendicular distance, then 0. Then plus, from here I have 8 times the perpendicular distance, which is 5. Because this one is 0 because the point where I take moments is in the line of action of that. So this would be 10x equaling 240. So here our x becomes 4 meters. And therefore, resultant force, our R is equaling to 10 newtons, comma, in the direction of, where it's in the direction of, you can say anti-clockwise, any. In the direction of, is that newtons, or you can say clockwise. Clockwise 4 meters. 4 meters from 4 meters from A. From A. And that will be. Now when you come to this, of course, you see this is bigger than these two combined. So if you resolve upwards, it's that our R is going to be 9 minus 2 minus 1 newtons. So our R here is going to be 6 newtons. So now, you see it's going to act upwards. So where should we take moments? Let us take them at C. So if I draw this diagram from here to this, when this is C, means that now I'm going to take moments. You can even take them at A. If I take them at C, this is going to be X. So, taking moments at C, in which direction? Let us take them clockwise. So at C, at C, so at C, which direction? Clockwise. Means that now, clockwise at C, you see this one is going in this direction. We have the force as R times perpendicular distance, which is X from here up there is X. It's going to be equal to, when I take moments about here, we have this one going this side. So I have 9 times, this is 3. This from here, the perpendicular distance from C is 3 plus this. Okay? Then plus, you see this one is also going clockwise. I have 2 times the perpendicular distance from C, because this one A, from C this one is going anti-clockwise, not clockwise from C. You see this one is going anti-clockwise. Let me show you. From C, you see this one is going clockwise from C. But when I come to this, from here, you see it's going anti-clockwise. So this is a negative, not a positive. So minus 2 times the quarter distance, which is 3. Then plus, you see this one is going, this one about C. This about C is there, but about C is going to be spread is going to go, so plus 1, this perpendicular distance is going to be 0. So our R is 6x equaling to 9 times 6, then minus 6. So minus 6x from here, it's going to be 48. So our x becomes 8 meters. So that's the distance of the resultant from the right of action. Therefore, we say, therefore, resultant force is 6 newtons and 8 meters from point C. From C, in which direction? In 9 newtons direction. As simple as that. Now, if someone decided to take moments here, would have got a different answer, a different distance from here, from this and then from this. If you take them here still, it would be a distance, remember, from here up to here. It's up to you. So the distance, these distances are going to always change depending on where you're taking moments from, because these are not couples. For couples, now this is going to be 0, but they are not couples, so that's why these are going to keep, the distance is going to be different. So that's it. I wish you well. Even for couples, moments will be the same. But now you see that these are not couples, that's why we have even resultant force. And that's how we use the moment principles, principle of moment. That's it. I wish you well. I think this note here can help you.